right, so today we're gathered to talk about high performance schools here at the TEMA conference 2020 virtual. I'm with Hendrix Consulting Engineers. My name is BHendrix. I've got my background in education is I've got a bachelor's of architectural engineering from UT and a master's in mechanical engineering from UT. Several certifications, professional engineer, certified energy auditor. You can read the rest down there. I'm a second generation MEP engineer, so I've grown up in this industry, been around it for a long time. I've been working here at Hendrix for about the last 25 years, since about 1995. So our goals today to talk about high performance schools and really any buildings. We want buildings that save energy and money, maintenance and hassle. And we want to talk about how we're going to do that with practical energy principles. So things need to be easy to control, easy to monitor, and easy for us to maintain. So one of the first things I like to bring up is, what does the Department of Energy use as a reference for the energy usage that we should see on these type of buildings? And so, today we're primarily going to talk about a primary, secondary school. Their reference there is 57 to 61 kilobTUs per square foot. So kilobTUs per square foot, for those of you who don't know, is you take all your electric usage and your gas usage, you normalize it into BTUs, move the decimal to get it in kilobTUs, and then you normalize it for the square footage of the building that you're using. So when we're talking about high performance schools, we want to see that number be, somewhere between 20 and 29 kilobTUs per square foot, which is about 50% less than the Department of Energy benchmark. Just to give you an idea, here's a graph that shows the SECO database for schools, and you can see how these pan out, and the Department of Energy benchmark is pretty high. So when we start talking about where we want to be being in a high performance market, we're down in the top 1% of all schools. So there's 5 steps that I like to talk about to get to, or 5 categories for having a high performance school, and they're divided among the building envelope. So what makes our building: walls, the roof, the glass, an efficient design of your MEP system and the application of that system, commissioning and engineered commissioning of the envelope and mechanical systems, power monitoring, how we can find the energy, find the waste early and help eliminate it. And then the last one, which a lot of you guys are involved in directly, is the owner behavior and the impact that the owner has on how this building runs. So as we talk about the envelope, the first thing we're going to talk about is we want to maximize our space while minimizing the surface area of the building. So what that does is it lets us reduce wall surface area, roof surface area, and window surface area. So we've got the smallest amount of load from the thermal envelope. So, a lot of that stuff we don't get to pick, but obviously if you can do 2-story classroom wings instead of 1-story classroom wings, you've got half as much roof area. You may have a similar amount of wall space, but you can cut the roof out, but a lot of times, does your site dictate how that building's going to be set out? That's true. Or does the district have preferences on how they want their schools to be laid out? Some people just don't want elementary schools that have 2-story classroom wings, and that's just kind of part of it. The other thing we talk about is selecting appropriate envelope materials. So a lot of times we talk about R2030, and what that usually is referencing to is the R value for our walls and our roof. So usually we're going to want an R value in the walls of about 20 plus or minus, and then R30 in the roof. Sometimes you're going to be able to get a little bit higher in the roof, but we'll talk about that here in a second. And then on our windows, you've got the various energy rating criteria, the U value, shading coefficient, also the percent of the glass that could be shaded and the orientation of that glass. And then you also want to talk about selecting the appropriate amounts of windows. And then finally, commissioning of that envelope, which we'll talk about later. So when we're talking about the heat load and the R value, a lot of y'all, may not look at this stuff every day. So what I decided to do was I've got this graph here, and it uses the square footage of wall for a typical classroom wing, not the whole school, but a typical classroom wing. And what you'll see is the tons of air conditioning or load on the vertical axis and the R value on the horizontal axis. And so you'll see as the R value gets smaller, the tonnage required to offset that amount of heat load goes up. So when you're down around an R value of 5, your tonnage is somewhere, between 60 and 100. And then as you move into a higher R value, the tonnage goes down and down and down. And what you're going to notice is the tonnage starts to flatten out. And so what we start to talk about is, well, how much does it cost me to get from one R value to the next? And what you'll notice here on the graph is it's pretty useful to start paying for an R value up to 20. And then as you get below 20, the tonnage that you're gaining for every 5 or 10 in R value number starts to diminish. So what we're trying to do is spend the money where it counts. So we do that same comparison for the roof. So what you'll notice is it's a similar curve for the roof. The numbers are just a little bit different. And this is the same thing. This is, this is a fixed amount of roof square footage. So it would ratio out to be a similar number, if you had a bigger school or smaller school or whatever. So this is all for a fixed volume here. And we got the same thing. So on the lower end, an R value of 5 puts us up almost close to 300 tons. And as we start moving down the graph, the bigger the R value we're willing to buy, we can get lower and lower and really get way below 50, maybe even close down to like 20, 25. So when you start looking at like an R30, it's pretty convenient to go ahead and pay for up to that R30 and pick up all the energy savings that you can. So whenever you're talking with your architect or building standards people or facilities people, or even if there's a cost savings measure on the table, you want to know how this is going to affect you in your air conditioning. So when we talk about glass, it's a little bit more, it's not quite as easy to talk about glass. So they have a few more variables. So this is for another fixed amount of glass. Right here, we've got 6,000 square feet. Same things for like maybe a typical wing on a classroom. And the way that this is divided is we've got the best values we can get in green for shading coefficient and U value. We've got good values in the blue. And then we've got really bad values in red. But you'll see that there's 2 bar graphs for each color. There's a reason for that. So the way the math works out for the load on windows, depending on your orientation and whether or not you're shaded, that load can change quite a bit. So they each represent the same amount of square footage of glass in various conditions. So let's talk about our best glass first. So if our best glass is facing west, we're looking at about 60 tons. If that same glass is shaded, we're down closer to 20, 25 tons. So shading makes a huge difference on the way the glass performs. And then, good is not quite as good as the best. And then let's talk about the worst. So if you get really, single pane glass that's got really bad properties, which a lot of the energy codes trying to keep you from using that stuff, you can see you can easily triple to quadruple the loads that you're getting from your glass. Okay. So the other thing that we would look at is if we combine the loads of all the 3 things we just talked about. So we combine the walls, the roof, and the windows, and we look at the load we would have for the whole building envelope, the glass can make a pretty big difference in how this performs. And so you know, your roof and your walls don't really care what orientation they're in, but your glass does. And so as we look, if we made good choices on a lot of our materials and we paid for the extra R value, you know, we could be we're probably about 130, 140 tons of envelope load for this given amount of square footage. And then as we are not willing to pay, or, you know, we choose lower values for all these systems, you can get up over 350, you know, you could probably push that up to 400. So it's pretty easy to see. You can over double the load just from your envelope that the AC has to work on every day, 24/7, right? And so these numbers don't go away ever. It's not like a people load that's variable. So it's really important on our fixed asset, you know, that we're making good decisions if we want to be energy efficient for the life of the building. The next thing that's interesting to look at is your square footage distribute. There's two graphs here. You got square footage on the left and you've got the load in tons on the right. So when you look at the left side, you can see, you know, 40,000 square foot of wall, 60,000 square foot of roof, and 6,000 square foot of glass. So you can tell, man, there is not a lot of glass square footage relative to these other two categories. But when you look at how much load is there from these three categories, it's kind of interesting that your load distribution switches on you. So your glass makes up the largest amount of the load relative to the other two. So your walls makes up the least amount, your roof is in the middle, and your glass is the largest load. So whenever you talk about, you know, spending dollars per square foot, it starts to make a lot of sense to spend those dollars per square foot in your glass, because you've got the biggest load to tackle as far as the envelope goes, is reducing your load. And the other two are still important. It's just that the industry is, you know, they're there on having R values that really are cost effective to get those loads down, where glass is still, you know, it's a harder nut to crack. So as we move on out of the envelope, we're going to move over and talk about HVAC system design. So we'll talk a little bit about types of systems, but primarily we're going to talk about system design, and we'll go over that, why we're doing that here in a minute. So we're got to take into account a lot of different things. Some of these things are fixed and outside of our control, and some of them aren't, right? So we've got the windows, we've got the quantity and locations of those windows. We've got multiple uses of the space, so we need to zone it for the use as well as the schedule. We need to be able to react to variable loads. We really want to be able to control outside air. So, you know, that's done through, there's several things to consider with outside air. One, you know, we can control the quantity with our CO2 monitoring. There's also technologies like bipolar ionization that give you the opportunity to reduce the required amount of CFM, but you still have to manage the building pressurization, and you want to maintain a net positive. And we want to do all this in an effort to not only keep the environment comfortable, but we want to minimize the possibility that there could be humidity issues and potential mold liability down the road. The other thing you really got to take into consideration is what's the appropriate system type for a given owner. Not all owners are going to be comfortable with every single system type. So the first thing I like to talk about is the way that the building runs is at different zones and different pockets of load. And so everybody here should know that the most efficient HVAC system that we have is the one that's turned off, right? If it's turned off, it's not using any energy. So we want to make sure we have a system that whenever we're not running the whole building, we can turn off sections of it rather than have to leave it running. So the first case we look at is, well, the entire building's running, so we need to run everything, and everybody needs all the temperatures, right? And the next thing we look at is, well, what about the condition where only the admin's there? So like summertime, after hours, principal's there, vice principal, whatever. And we only want to run this small square footage of the building. If we selected a system that you have to keep the entire building on, or chunks of the building, then it's going to be less efficient to run the whole building than it would be just to run a couple of small units for the admin. Another place that has varying uses by time is going to be the cafeteria. So, when we're talking about elementary school, we really want to be able to run that before and after. It goes with the kitchen as well. Those can be used for after hours events, before school, after school, all sorts of stuff. The gym is the same way. Most schools are trying to produce a little revenue by doing YMCA rentals, after hours programs, all sorts of things. And the most efficient way to run that is if it's got its own unit and the rest of the school can be off. The kitchen staff usually shows up early in the morning. They start cooking early. And so if they show up at 4, it's better to be able to only run the kitchen at the conditions they need rather than trying to run the entire school. And then everybody knows the library. One of the interesting things now is, how much longer are we going to have libraries with books? But currently, we still have lots of books, especially in the elementary age, and humidity control is very important so the books don't get ruined. That paper and all the bindings can really get out of control, especially during the summer, if the setbacks are such that the humidity gets too high and the temperature gets too high. The other thing we generally are seeing is most districts still want all the classrooms to have their own thermostat control. So there are some instances where you may run a unit that runs a whole wing of a classroom, and then there's some other instances where every classroom has its own unit. We'll talk about both of those here in a little bit. But it's really important to give them their own control so that you don't have 2 teachers fighting over who's hot, who's cold, all that kind of stuff. So let's talk a little bit about the different systems. So you've got several pictures here. We've used all these. You've got chiller systems up on the upper left. We've got some water source heat pump systems in the middle. And we've got VRF or standard air handlers on the right side. We've got rooftops on the bottom left. And it's important to note that pretty much every conventional HVAC system today uses compressors and refrigerant of some sort. So I know a lot of times we talk about different systems that use water, but that water passes through a refrigerant heat exchanger at some point, and refrigerant is used. So pretty much every air conditioning system that we use today is some version of a DX unit, even if it does use chill water. It uses refrigerant somewhere. We've got single stage, we've got 2 stage, and now variable speed. Typically, the more stages that we're allowed to use, the more efficient that we are. So another thing you're going to notice is I wouldn't necessarily say that any one of those systems in particular has the market locked on the most efficient. So here's just a couple clips from a few manufacturers that we see all the time. So you'll see you can get a rooftop in 3-ton range that's running an 18 SEER or IEER. And then you can also pull ground source or water source heat pumps, and they can have similar ratings, 17. You'll notice too that the efficiency rating changes based on the water temperature for the water source heat pump, just like it would for the air temperature on an air-cooled device. So the way this manufacturer listed, they list the water loop if you're doing water source at 86, but they list the ground loop at 77. The reality is the difference between those two is the temperature. So if you had the ability to run your water loop colder, then the efficiency would go up. If your ground loop gets warmer, then your efficiency would go down, because the physics of that unit are the exact same either way, right? We're just riding an efficiency curve based on temperature. And you'll see the same thing for air-cooled equipment. In fact, this is a comparison that we looked at. It is efficiency ratings for a typical 3-ton classroom unit. So a lot of times we're going to see the outside air decoupled from the normal heating cooling unit for the classroom. And you can see we would apply them this way. So if you look at that water source unit, which is the blue line, you'll see as the temperature on the bottom gets colder, the efficiency goes up. So we got the efficiency on the y-axis and the temperature on the x-axis. But you'll notice that's the same thing for a 2-speed rooftop, which is the red line, and the green line, which is a traditional split system, also in a 2-speed. So as the air temperature goes up for the air-cooled equipment, their efficiency goes down. As the air temperature gets cooler, the efficiencies go up, just like the water temperatures for the water source stuff. So you've got similar things. So what we usually like to talk about when we come back to which system is right, I mean, you really got to talk to the owner and see what they need. What kind of maintenance guys do they have? What kind of training programs are in place? Are they far away from any service technicians that they don't have any on staff? So, you know, some of our clients are a one-room school, and that's the whole district. And there's only the custodian and the superintendent are, you know, sometimes the same person. And so for that district, you know, everything has to be very straightforward. It's traditional split systems, something that a residential AC tech could fix, because there are no commercial techs within, you know, 60, 70 miles of this town. But then you move all the way up to a district that's got 5 or 6 high school campuses and, you know, 30 or 40 elementaries, and they have techs that can work on everything. So, you know, you really got to talk to the district or the owner and see what are they comfortable with, because really what they're qualified to keep running the best is what's really going to give them the best efficiency. And you can see from these other slides, all these guys are all fighting for the same efficiency dollars. So we know that Trane makes every kind of air conditioner there is. They haven't picked just one. So I don't expect for one type to just rock the market, and that's the only one anybody's ever using, because that would have already happened by now. So all these different systems, they have their place, and a lot of it depends on the architecture of the building, space available, the roof system, all that type of stuff. And so we're going to go through just a couple of quick examples. What we got on the screen now is a 2-story masonry building. It's got a low slope, or sometimes called flat roof, but we know no roofs are supposed to be flat. This particular one was primarily rooftops with decoupled outside air. And so you can see that they did a rooftop per classroom. There's quite a few rooftops, especially on the 2nd story. So, you know, you got to account for chases up and down for air, uses up a little bit of square footage. But all that just has to be coordinated into the architectural system of the building. Right here, you'll see a school that in Maynard. So this is a 3-story class. This has a 3-story classroom wing, and with some big box spaces that are double high. And I don't actually think there's any 2-story, any single-story spaces on this. So along the left-hand side of the boomerang that we like to call it, that 3-story classroom there, the district chose to go with VRF. So this worked pretty well with the 3-story classroom wing, because we're able to compile all the heat rejection equipment. On the lower left, you'll see the condensing units on the roof. And the footprint of that was favorable, because as you get taller, you run out of roof space. And then you'll see behind a couple of those heat rejection units, heat recovery units that make up air. So they had dedicated outside air. We coordinated chases to get the outside air down to all 3 floors, but they just had indoor air handlers that we'll look at here in a second that served each classroom. Now, when you move over to like the band and the arts and the gym areas, you'll notice that those are rooftops. And so, you know, there's nothing that says you have to pick one specific HVAC technology for the whole building. You know, in this case, they had different preferences based on what was happening with the architecture and sticking inside what their maintenance staff could work with. And so we have a combination here. We've got VRF in certain places. We've got rooftops on other spaces, and then we've got the dedicated outside air machines to handle that outside air load. This is another school that was 3-story. For the same reason here, they went with VRF for all the classroom areas, and then roof RTUs on the big box spaces, and then dedicated outside air as well. And you can see it cleans up the roof quite a bit. This particular example is a example of an owner that had they wanted slope metal roofs. It's a 2-story building, and this is a good application for VRF, mainly because it allowed us to not have to have any rooftop equipment. and allowed us to do all the heat rejection equipment on the edges of the building. So you'll see there's an equipment yard on the far right, and there's a very small equipment yard on the far left. They're notated up on the pictures at the top. So the equipment yard on the far right is the upper right-hand corner picture, and the small equipment yard on the left is the upper left-hand corner. And then you'll see they had a mezzanine here shown in the lower right picture where they had standard style air handlers with ducted supply and free return. So we'll move over to talking about lighting. So I'm sure most of you guys now are seeing LED coming on pretty hard. If you built a new school in the past few years, there's a good chance you've really pushed it towards 100% LED. When it first came out, you know, it was mainly a maintenance argument for cost, 50 lumens per watt. Many people in this room can remember when fluorescent was 50 to 70 lumens per watt. So at first, LED was not as efficient as fluorescent lighting, but that's changed. So now we're seeing efficiencies up to 170 lumens per watt. It may even be higher now. So now you don't just have a maintenance argument for the life of the LED, you know, hopefully lasting 10, 15, 20 years. You've also got quite a bit of energy savings. So where we used to see a 2x4 fixture, you know, running 90 watts a piece, now we're starting to talk about 40 watts. Sometimes we're talking 35 watts and maybe even lower depending on what we're doing. One of the things that does start to mean is that with all these lights having different lumens per watt, almost, you know, every 6 months to a year, whatever fixture you used a year ago, you may not be able to use the same fixture again. So it's really made prevalent computer modeling of the lighting layouts, the lighting spacings, the heights that they're at, the lumens, the watts, all that stuff, all's got to be modeled more frequently now, because used to, you know, for years and years and years, you had a 3-watt, a 3-lamp T8 2x4 fixture, and you knew that you used it on an 8x8, and you got 8x8 spacing, and you got a certain number of foot candles for a 9-foot ceiling. And if you used 10x10 spacing, you knew you got this, you know, this foot candles on the desk. Well, now that's all changed, because every 6 months to a year, now it's not 50 lumens a watt, it's 70. Now it's not 70, it's 90. Now, you know, so you're just seeing these things. A lot of 2x4s now, I think they're probably in the 120 lumens per watt, 130 lumens per watt range, and I expect it to keep climbing. So we're starting to see where the code used to allow 1.2 watts a square foot just for lighting. We're starting to see those drop. You know, a lot of them are getting below 0.7, starting to creep up on 0.6 watts a square foot, and sometimes a little less. The geometry of the building will change that. You know, the higher the ceilings you have, that's going to go up, because it takes more light to get down to a floor that's further away. One of the big things you got to pay attention with on these LED lighting systems is glare. The diodes can be pretty intense. You'll really notice it in gym situations. If you don't use the correct lensing, that can really be distracting to the players, whether it's volleyball or basketball. It can really be irritating. So you really got to pay attention. One of the other kind of cool things now you see on the lower right, we're starting to be able to get different shapes with light fixtures, and it's become pretty prevalent. They're also able to, you know, they're getting smaller and smaller too, and the shapes are getting more and more prevalent. So we're starting to get a lot of different cool stuff we can do. The last thing that is really starting to become a little bit more prevalent is tunable white. So last time I checked, there was about a 50% premium. We still see some people considering it in certain areas, certain people talking about it as alternates for the whole school or just the classrooms or the admin. And I probably should stop here and make sure that everybody knows what tunable white means. And so what that means in a general sense is white is not always white. So if you've ever been to Home Depot and you're walking down the light bulb aisle, you'll see they have a display, and it shows different white lights measured in different Kelvin temperatures. The higher the number is towards the blue spectrum, usually called cooler or daylight, and then the lower spectrum is towards it's called warm. It's maybe a more orange. Traditionally, incandescent lights were around 2,700. Most people are used to about 3,500, maybe 4,100. So that's generally what you see. So they're starting to say that those the tunable white, those different white spectrums in the Kelvin rating can affect your circadian rhythms, behavior, productivity, special needs areas. And they like to, they've talked about using it a couple different ways. So when the sun rises in the morning, you get more orangey light. Midday, around noon to 3, you're really in that blue light. And as you get back towards the evening, you go back towards the reds and the oranges. And so what they're saying is, if we always have the really bright blue light, it can mess with your energy production and it makes it hard for you to go to sleep. It's why people talk about messing with screens, iPads and iPhones at night when you're going to bed makes it harder to go to sleep. Same reason the iPhone has a night shift mode on your phone. If you haven't seen that, you should do a quick search on that, and you could set that up so that it'll reduce the blue light that you get in the mornings and the evenings. One thing to keep in mind is you're going to have a lot lower selection of light fixtures as you start to look at tunable white, but it's out there, but it's, that's going to be a whole nother presentation. The other thing that's really become a big change in the lighting industry as far as the performance of these systems goes has been the controls. So right below this picture, you'll see me reference the IECC 2015 as a state minimum. So a couple years ago, the state set the minimum energy code as IECC 2015. And the reason that matters to us is they mandated an auto off but manual on for lighting control. So that means you have motion sensor in the room, you leave the room, it automatically turns off. No big deal. We've been doing that for a long time. The kicker is when you come back, used to with the regular toggle switch, it stayed in the position that it was in when you left. So if the light was on when you left and the switch was in the on position and the motion sensor kicked it off, as soon as you walk back in, the motion sensor turns back on because the switch is on, right? It's a manual device. So the code doesn't allow for that anymore. It has to be a manual on, which means that switch has to be resettable. So standard line voltage toggle switches are not resettable. Now you enter in the low voltage device market. So here you've got a sample of various button styles, couple different manufacturers. If you haven't built a new school recently, you may not have seen these, but the next time that you do, this will be something that you need to talk about. So there's been a lot of electricians that have been mad at me. They do not like to see these come. Unfortunately, they are the way that things are going. So I think they're here to stay. One of the really good things, though, there's a lot of positives to get out of this. So if it's done right, they can be pretty simple. They're very functional, and there's an opportunity for quite a bit of savings. So one of the great things is every LED light inherently is dimmable. So with the correct lighting control, and you'll see here, there's several that have an on-off button and an up-down. So now in the past, where you used to have to pay an extra $100 to $120 a fixture for a fluorescent dimming ballast to get dimming, well, you're not having that anymore. So you bought a $150 fluorescent light or a $100 fluorescent light. You added $100 to $150 for a dimming ballast, and now your fixture's $200 to $250. Okay. Now, didn't used to be, but the LED lights now they're $120, $100 for a 2x4. They're already dimmable, so you get the dimmability without spending any extra money. So that's really nice. It gives you some flexibility on programming for zoning of special areas. The on-off motion does not appear to affect the LEDs as much as it did some of the fluorescents. Some of them would die early from the on-off cycles because of the gas in the tubes. The other thing that we will talk about is we're allowed to do motion to a dimmed level, which is pretty cool. We'll look at that here in a second. Photo control is pretty easy to do. But one of the things you have to start thinking about is, do you want your lighting control for the whole campus networked, or are you good having it localized to a single room? Most of the districts that we're working with, they tend to lean towards the single room control. I'll talk about why that is here in a minute. And then you've also got a couple choices on, are you going to do onboard controls for fixtures, or are you going to separate those? And then when we're talking about exterior light fixtures, are we going to do time clock Or do we want to go ahead and hook those to the BAS now? Or do we want to just have it all be on board? So in this picture, one of the things that's really come up is that not all lighting control interface is equal. This really affects your performance in a couple ways. The picture on the left, even though it looks a little grainy from what I'm looking at, it's the user interface is very intuitive. The on-off is clear. The up-down arrows are clear so that the user is very comfortable without having any knowledge of what's going on. They can they can turn the lights on, off, and they can dim them. So a couple of projects we've been in where the ones on the right, the picture that has got the blank looking switch on the right, it's the left picture on the right side. That is an on-off and a dimming device that you have to know how the programmer decided to program. If you hit the top or the bottom or hold it or don't hold it, it's very hard to use. And so what we've seen on those is people just don't mess with them because they turn the lights off on everybody. So then they don't dim them as much. And when you don't dim them, then you don't get to save any energy. The one on the far right is a motion device with the on-off up-down built into it. And we've got the same issue there. It's not intuitive. There's an up arrow and a down arrow, but when you push them, it's hard to understand. Are you supposed to hold it to have things dim? Are you supposed to tap it? How exactly are you supposed to do that? Where if you look at the three in the left picture, that gray one is a motion sensor that also has a on-off up-down button. So with that one, it's very easy. Oh, here's an on-off button. Here's an up-down button. I'm not turning the lights off on everybody in the classroom or in my office area. The other part of this, the low voltage stuff that you're going to start seeing is you got a couple different items. So you've got a power pack, you've got your motion sensors and photocells, and what you're going to start to learn is the way these lighting systems are set up. You're going to have Cat5 between your low voltage switches, which are shown here. That'll go up the wall to your power pack and over to your motion sensor or photocell. And then from your power pack, you'll have line voltage that goes out to the fixture. And you'll also have dimming wires that go out to the fixture. There are some instances where basically the power pack is built into the fixture and you'd go Cat5 from fixture to fixture. But they're just different scenarios. Typically, this is what you're going to see. So you're going to start to have a lot more Cat5 above the ceiling. The other thing that's kind of interesting now is a lot of the companies have, like this shown here, the Bluetooth radio. You plug that Bluetooth radio Cat5 into the switch, or actually any one of the devices, they all have an in out on them. If you look closely at the power pack, you'll see there's 2 or 3 Cat5 cables in there. So you plug one in there, and then there's an app for your phone, and then you can do all the settings for the classroom, save that as a scene, call that scene classroom, and then boom, 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 go program all the rest of them, and you're off and running. One of the good things now with all this stuff is, earlier we talked about the dimming. If a teacher decides that she likes her lights at 70% is like a good normal level for her to teach at, when they leave or turn the lights off, whether it's motion off or manual off, when she comes back, it turns on to the last setting. So it comes back on at 70%. So even if you were designed at, 0.6 or 0.7 watts a foot, you may ultimately be using 60 or 70% of that if, because of the materials in the room and the way the spacing of the light is, it's more comfortable for that to be dimmed at 70%, and that's good enough for everyday use. So you actually can save a lot of energy just because you've got the ability to dim everything. We'll touch on exterior lights a little bit. I mean, the controls on those have come a long way. So we used to just do time clock and photocell. And you'll see on the picture on the left, the little white circle underneath that fixture, that's an onboard photocell and motion sensor specific to the height. So, they're like up to 20 feet is a certain sensor, and then from 20 to 40 feet is a more sensitive sensor. One of the cool things there, you can still run all these lights on one circuit and run them to a contactor, connect that contactor to your BMS, and that way you can control the schedule from your BMS or a time clock, either way. We used to run multiple circuits around the site, do the ones close to the building as zone A, the ones away from the building as zone B. That way at a certain time of night, you could turn off 2/3 of the lights and save some energy. Well, now this is a lot easier. You just select a fixture that lets you have an onboard photocell or motion sensor. And as there's nothing going on, the motion sensor will allow them to do a couple of things. Either turn off, maximum energy savings, lowest security, or they also will motion to dim. So you can program them to say, no motion in 15, 20 minutes, dim down to 35%, but I don't want you to go off. And so what can happen is, as it gets dark, photocell brings on the lights, people are coming and going, lights are at 100%. As people leave and things stop happening, motion goes away, the lights are triggered, they all dim to 35%. Rest of the night, they operate 35%. You save 65% of the wattage for the whole evening. So that happens on, you can also do that on certain wall packs, but you got to be specific when you're picking these fixtures out. Not everybody offers that. So you just got to be aware. This is also really helpful in conditions where you might have neighbors. A lot of elementary schools are built in neighborhoods. So you want to be sensitive to them. That onboard motion dimming is very favorable to being a nighttime friendly neighbor. Some of these LED light poles can be very intense. And, you know, if the considerations aren't taken to avoid view angles and glares and things like that, you can see one of the options is to put a super sweet light blocking hood on your sleek, low profile LED light pole. So periodically that happens. It's not, you know, the most aesthetically pleasing, but if it makes you have a happy neighbor, then sometimes that's just how it goes. Okay, let's talk a little bit about commissioning. So what is commissioning? Who can do it? What's it for? So back in the 2012 Energy Code, it became code to have a commissioning agent provide commissioning services on buildings of 40 tons and larger, roughly, of air conditioning. So commissioning is a professional service. It's similar to engineering or architectural services. It's a negotiated scope and fee. It is not a biddable item, at least not for a public entity. For private entities, that's different, but generally it's still a negotiated scope and fee. The contractor cannot provide commissioning services. Their startup and checkout is not commissioning. That's a separate service. That's what they're doing. That's part of their install. So the commissioning service is the performance verification of the contractor's installation. So your commissioning agent, unless you're asking them to, per the Energy Code, they are not doing any engineering verification. So it's not their job to double check your engineer's design, calculations, anything like that. They're strictly there to do performance verification on the back end of that the contractors installed the system to meet the requirements on the engineering documents. So one very important distinction is the engineer of record can be your commissioning agent. So they're two separate things. Sometimes you'll hear people say that's the fox watching the hen house. So the way that would be the case is if you have the contractor doing the commissioning so that the installer is doing the commissioning, because all that's being checked is the installation, not the engineering. So having the engineer be the commissioning agent, if that's what you choose to do, they are third party from the installer. So unless the engineer works for the installer, they're already a third party to that. So they're allowed, and code does not preclude them from doing the commissioning. The other thing you want to make sure that your commissioning agent has is some experience in system design and how things work. Over the years, there's been a lot of people change industries from other engineering areas, some from NASA, some from petroleum, and hop over into the building environment and go get a commissioning certificate and call themselves a commissioning agent. That's not worth anything to you if they don't know how these systems work. So you want to make sure the person that you're hiring to do this, number one, knows how to do system design, maybe is a current engineer on systems as part of their services, and can troubleshoot these things. So one of the things we like to talk about is people wonder, well, why would I want to do commissioning? Everything's supposed to work when the contractor installs it from day one. And while we all wish that was true, the complicated control systems, mechanical systems, and test and balance that we now have, things just aren't always optimized when the installation's finished. So here's a little bit of an extreme example, but we had a client whose energy for their elementary school was really high in their opinion. And so we went and reviewed some items with them. And one of the things that had happened was the controls and the units weren't set up correctly to listen to the control system. And so we asked them to check, see if their stuff was running at night. They said the control system said it was off. So we drove by the elementary school in the middle of the night. All the air conditioners were running. After we had a proof of concept there, they went back and checked, and these units had not had the dip switch and the controller set to listen to the control system. So they did that. The first year, they saved $83,000 in electricity and about 17 in gas for a total savings of $100,000. Unfortunately, that school had been running like that for about 3 years. So you can see, I mean, the cost of not commissioning is far exceeds whatever it costs to get commissioning done. You can see the before and after graphs. The red is the before and the blue is the after. So a lot of people ask how much commissioning costs. This slide doesn't account for some of today's larger elementary schools, but the ratio still remains the same. You can see from this that the commissioning cost is very relatively cheap, obviously compared to the building cost, and even compared to the design fees, it's a very small number. What we've got here is, if you were to look at the typical cost for commissioning maybe a standard elementary school and versus the energy usage. So you've got 4 different bar graphs here. The blue represents the optimum energy usage over 5 years, what that cost might be. And then the red represents potentially wasted energy if things are not set up correctly. So you've got a couple different scenarios. You know, on average, in the middle, you're going to have, you know, you could waste maybe $250,000 over 5 years. If you're one of the unlucky ones, like that other school, you could be wasting 100, 150, maybe more per year. So over 5 years, I mean, you could easily waste $600,000-$700,000 versus if your system's commissioned, all the things are set up correctly, everything's calibrated, you could be hundreds of thousands of dollars ahead on your energy budget or your M&O budget, however you want to look at it. Depends on how you fund that. So you can see, for less than $100,000, you can save a ton of money ongoing into the future. It's generally going to be a good idea, after a certain amount of time, to have somebody come back and do a little bit of retro commissioning. We'll talk about here in a second. But you really want to do commissioning up front and do retro commissioning only as a maintenance item. So we're talking about commissioning 2 different things. Not a lot of people do the building envelope. It's really a nominal cost to get done for what you get. We're going to talk about the envelope, which is where all our energy efficiency starts. We talked about the math and how we get there between the walls, the roof, and the windows, but also how that goes together and performs is just as important as the HVAC system itself. And then the second item is the HVAC system and the controls, installation, construction, and the performance verification. So when the envelope's going up, one of the things, if you choose to have that done, which this is not code required, it's an optional service, but we get a lot of clients that ask for that. You go and you'll be looking for places where the envelope is broken. So here we're looking at, drain plane issues where DENS glass is busted, it's not continuous. You'll also see other items where you can't see from the outside, but insulation was missing. So having somebody that is looking in the different areas to make sure that the insulation is continuous through the building. And this is just an example of, we found this with a thermal camera, and there was a whole section of a 2-story wall that was not insulated that we were able to find, and they were able to remove that and get the insulation installed before the building was completed. There's areas where there's rain leaders being put in, and for one reason or another, they cut the DINS glass to get the rain leader in. So you've got drain plane breaks as well as thermal breaks. So the other thing this helps you prevent is reduces as much as possible water intrusion into the building, which helps prevent, possible mold outbreaks in the future or just water damage in general. And the only reason that Tyvek is cut is because we cut it. So the Tyvek covered this up. So they were moving on. So that DINS glass was going to be left cut, and the Tyvek covered it up. So if we hadn't seen that before the masonry went up, then it would still be there that way today. Here's a spot where they were putting a canopy, welding a canopy onto the wall after the DINS glass had been put up and the moisture barrier had been painted on. And for whatever reason, this genius in welding decided that the way he was going to find the structure was he would just go along and he would tap the welder where the canopy met the wall and try to find the structure behind it by burning through the DINS glass. And so there's a bunch of locations along that canopy where he burned holes in the drain plane that, unless somebody documents that they need to go fix it, sometimes that could get left. Then as we move into the controls, there are so many things, and you're seeing that here. There's I think on this page, there's close to 20 items that need to be verified just on one unit. Verifying that the info here is real, that the points are landed where they're supposed to be landed, that your temperature reading in this, like number 14, is it really 70 degrees in the space, or is it 74? And one of the things that's important is, as we tighten schedules, as we tighten set points, we put limits on, we're only allowed to cool to 74 and we're only allowed to heat to 70. As we do that, if our sensors are not accurate, then the occupants become uncomfortable, and we'll find ways to get around that. You got to check, are all your stages working and all your cooling? Are all your heating stages working? All these different items. Is this information that your energy managers and your controls people are making decisions about how to run the building? Is this stuff accurate? One common thing that comes up when we're commissioning is checking the outside air machines. So here's a quick thing that we found on one job, where on the left, you'll see that the makeup air unit at 11:37 p.m. is discharging 54-degree air. Obviously, nobody's at school at 11:37. One of the RTUs that was getting fed by that space, its space temperature was 65, which is well below the cooling set point, especially in the after hours condition. And so we were able to identify that makeup air had been running and it was stuck. For some reason, it was locked on. And so, you may not think that's a ton of energy, but this particular outside air machine or group of outside air machines, a school could easily have, 10 or 20,000 CFM of outside air. The equation for that energy is 1.08 times the CFM times the delta T. So in that school, there was, in this example, there was 20,000 CFM. The delta T, it was about 85 outside. It was cooling it down to about 55. So there's our delta T. You run all that down and you get BTUs per hour converted to kilowatts per hour. And then we know that at 10 cents a kilowatt, that could cost you $19 an hour to run that machine. And so as you run that over days and weeks, now all of a sudden you're starting to say, oh man, could cost us $2,400 a week. So there's a lot of energy waste that could be happening if these machines are not running properly. And so the traps can be run on that several ways, but identifying that exists early on is a way that you can really prevent the district from wasting a lot of money on energy. Another thing you got to check, we were talking about that a minute ago, is the sensor verification of the classrooms. So in this particular wing of units, 64 of them were over a degree to a degree and a half out. I was at another space. This was an office building recently where 100% of the sensors were off, and they were off by 3 to 4 degrees each. They were all reading high. So the temperature was set at 73. The entire space was at 68 to 69. This becomes really important as you start to really use the controls to really lock down how the building's used. If they're not accurate, then you're going to have unhappy teachers, clients, you name it. We use a lot of different tools as we're doing commissioning. Not only are we using the computer, you've got temperature sensors, we've got thermal cameras, flow hoods, humidity sensors. We've even got several data logging devices that are used. A lot of times you may wonder, why are we going to do that? Well, if you've got a technology guy and he's complaining that his servers are too hot because the air conditioning in the IDF room's not good, but you've got dedicated AC in there, we put a data log in there and we let it run for a week, and you can show him that you maintained 65, 70 degrees 24 hours a day for a week. All of a sudden those complaints magically go away when you can show them some data. Also, if you're having troubled areas, it's nice to be able to leave those in a space for a while and then come back and help identify what those are. So I mentioned retro commissioning earlier. The best case on using this is you've commissioned on day one, you're 5 or 6, maybe you're even 8 years in the future, or could be 2 years in the future, but for some reason you're noticing a trend up in your usage of energy and you want to bring it back down. That's the best way to use retro commissioning. If you try to get by without doing commissioning at first, you're like, if we have problems, we'll just do it retro. Well, the benefit of doing it on day one is all your contractors are still under contract for their 1-year warranty to make everything work as it was intended to work. When you do it 5 years down the road, you end up with a 2-phase process. The commissioning agent's going to go do a survey of the building and identify problems. But identifying those problems, there's still got to be somebody to fix them. So some things may be able to be reprogrammed. It's not that big of a deal. You may still have some controls programming you got to pay for. But if you find other issues, you may be in a situation where those problems may need design engineering documents, which is a cost. And you may also, and you need those design documents so that a contractor can come in and make the adjustments or the changes required to the building to fix that. So all of a sudden, the cost to do all that stuff increases potentially exponentially, where if you do it when the building's brand new, all the contractor costs are already included in their construction of the building. The other thing that we talk about a lot on this is how that contract is held. I mean, we can say that discussion for another time, but sometimes these contracts are through the architect, sometimes they're direct with the owner, and sometimes we're doing them direct for the construction manager. It just depends. Another place that is really important to save energy that we've been doing probably since around 2009 timeframe is power monitoring. So what this does is helps you find out where the energy goes, when it goes, and why it goes. If you're just doing it when the bill arrives, depending on how you see the energy bills, you're always looking at 30 or 60 days later. So if something's broken or something's been put in a maintenance bypass, or just different things that happen in a building that could, with air conditioning, that could drive the energy up, you're always playing catch up. So the way that we like to break that out is through strategic power distribution. You lay out your electrical panels in such a way that you can monitor the total building energy usage. Maybe you just want to look at your HVAC only. Maybe you just want to look at your lighting only or your low voltage. So we like to be able to break it up in those 4 categories. Sometimes we'll break it out in those 4 categories by wing of a building or by area of a building as well. That lets you do a couple of things. With a couple clicks of a button, you can start to get an idea for how your building's operating. Proportionally, what's the higher user. It's going to let you identify problems, identify high usage areas, It'll help you identify if maybe the scheduling's messed up on certain wings. So you can take corrective action quickly and make informed decisions. Most of the control systems out there are also going to give you the opportunity to have an alert if something is getting out of whack. One of the ways this might show up on your front screen, you might just have it where it has your main demand. So you see the building electric meter here, the lighting usage, receptacle usage, HVAC, and in this case, the owner asked us to break out the gym since they like to bill it separate. Same with the cafeteria. We're also asked to break the kitchen out a lot in case you're in a district that gets federal tax credits. It makes it easier to go back and get those if you've got that stuff all data logged with your power monitoring. So the where. So here you can see the different colors represent full building in green, HVAC load in orange, lighting load in blue, and plug load in red. So real quickly, you can say, man, out of my total energy usage, where's my cream to save money? In this case, this building, it's HVAC. This is a full week, so you can see, on the weekends, there's still some stuff going on. Some lights are still running on the first day, and then as you move, when all the people show up, it's all air conditioning load. So once you can track this week over week, you can start to see if how weather's affecting you. You can make sure you're turning this stuff off on holidays. If you've got a 3-day or 4-day weekend scheduled, if you have somebody available, they can check and see, oh, look, we didn't schedule the holiday. Let's hurry and get that scheduled off. Maybe you can set some alerts so you get an alarm if it's a scheduled holiday and the KW reaches over a certain number, so somebody can make sure and schedule all the AC off. So the previous graph is cumulative kilowatts in a day. This is the actual demand over time. And you can see here, the total building is really fluctuating based on the air conditioning load. The lights is pretty straightforward. Maybe there's still room for improvement, but over time, you'll be able to notice if things start to get out of the normal for you. This also lets you look time of day. So if things aren't scheduled off at night, obviously the individual days would just drift together as one big lump on the graph rather than an individual day being a spike. You can also probably start to notice too how your early outs affect you. Are you turning your outside air off when you should be? There's a lot of different things you can start to dial down once you've kind of got this data at your fingertips. So the last thing we've got is the high performance owner behavior. So this is where, energy managers and maintenance personnel they're the key here. I mean, they really are. So, you could have bought and paid for, good equipment, great engineering, great commissioning services. But, if on the back end, there's not staff that's dedicated to making sure that this building is turned off when it needs to be turned off and, on when it's supposed to be on and things like that, then, the energy usage can be doubled or tripled just from the owner's usage. And, that would show up here in your power monitoring. If you, like that first example we talked about with commissioning where the units weren't tied into the control system correctly, I mean, this graph would look ridiculous. It would just go up and stay up, A lot of the things y'all are going to really be focusing on is making sure that your filters are routinely changed because, as they get loaded up with dirt, the static goes up, so the energy goes up. This is going to really vary a lot campus by campus and equipment type. So your outside air machines may have to be changed more frequently than your, space use equipment. You're really going to want to make sure that your staff is knowledgeable on the equipment that y'all are using. Do y'all have ongoing training? Are they training on chillers? Are they training on rooftops or water source or VRF or, what is your staff knowledgeable on? Do you even have that kind of staff? Do you have to outsource it? If you outsource it, are you budgeting properly to get routine maintenance done by an outsourced company? All these things are really going to affect the performance of your building. Do you have somebody that's familiar with your controls? Are they going to ongoing training? Can they look at the controls and know what they mean? Or is it just, pictures on a screen? Is there good communication between your departments? So, a lot of times you're going to have some conflicting. Really, we all have the same goal, but sometimes the way we get there seems to conflict a little bit. So, is your energy management, maintenance department, your facilities department, and your campus staff, is everybody on the same page? Do they understand how the schedules are set, what the set points are meant there to be? Is the campus letting you know when they need maintenance done? Is everybody clear on how the overrides work? Is the maintenance staff making sure that when things can't be fixed, they're not left in an indefinite override? I mean, you just got a lot of factors. And so making sure that there's good communication across all those groups is really going to help, hone in your building's energy usage. And then you want to make sure that you're scheduling preventative maintenance. New campuses, once the bugs are worked out, it's, sometimes we forget about it a little bit because they don't have the little nagging issues, but all of a sudden they're 5 years old, starts pressure, and on top of it. On the energy manager side, you're going to be watching the schedules, trying to keep those schedules as short as possible, and the run times. They're always going to be trying to raise those cooling set points as high as they can and lowering the heating set points as much as they can. But we know that, they can only be raised and lowered to a point. Otherwise, people will cheat and find a way around them. They'll put light bulbs or little heaters or coffee pots or something next to the thermostat so they can be cooler. But that becomes really important that we have everything calibrated so that when we say that we want, if 74 is our cooling set point, then we want to make sure that we're giving them 74 and it's not really out of calibration. They only get 78. You don't want to put people in that position. It's really nice whenever your outside air is decoupled, because then you can schedule your outside air units for only when kids are there. That way you can run your heating and cooling set points. Maybe you run those from 6 to 5 because you've got admin staff early and cleaning staff in late, but you're only required to have the outside air for the kids when the kids are there. And that might only be from 8 to 3 or 7 to 2. And so now you can pick up, 3 or 4 hours of energy of those outside air machines by turning them off. And over time, if you're saving $20 an hour for 4 hours a day, times 200 school days or 180 school days, man, that really starts to add up to some money. Verifying that your schedules are actually working through site visits periodically is really going to be important, because things do get turned in on, stuff does happen. Sometimes you think you've got your schedules in there good and stuff's going to be running 24/7. And if you don't periodically check that out, there's no way to know. The use of power monitoring and data logging is really going to be a good tool for you guys to be able to see things from your computer and try to keep tabs on what's happening on multiple buildings. It'd really be good for you all to attend design meetings, even if it's just 1 or 2 in the beginning of some of your new campuses, to really communicate to the design team, what are some goals for the district or the owner, and how can they help you meet that? What's important to you guys as an owner to keep things moving forward with a really energy efficient design. And you may be able to also remind some of the architects to keep the quantities of glass reasonable. I know that some of the entries in the stairwells really look like they look beautiful as walls of glass, but sometimes that can cost you 20 to 40 tons worth of air conditioning just for those areas. And, the stairwells that use 20 or 40 tons of glass are still just stairwells. So from an energy standpoint, you've really got a competing effort there. So just to recap, you really want to be in the driver's seat on energy. I mean, it's very possible to get your campuses down in the 20s. Some people say they'll shoot lower. In our climate down here, that this is a good number. Most of the people that are hitting below 20s, it's some sort of one-off campus. It's not fully utilized. There's something else going on. I mean, if you're getting in the 20s, you're doing good. You've got your outside air on. You got your schedules good, things are running good, you've got good equipment, people are paying attention. You know, maybe you're running some games between campuses or between teachers because you've got power monitoring. You can have the 5th grade try to beat the 4th grade on their energy for the week or the month or whatever. But this target, you know, compared to the national benchmark, is a huge savings, and really it can mean a lot to your district. You can save a lot of money for other programs. So I've got some of my contact info up here. I've got my email address, Instagram handle. Pretty soon we'll have a YouTube channel with some videos with content like this if you're interested. But here shortly we're going to move on to the questions from the chat box.
Hey everybody, we are here. If you guys have any questions for Byron, I'm going to go ahead and let you ask them. I am going to mute my side. We had to combine rooms and switch computers because Cami was having issues with her presentation. But if you have any questions, please put them in the chat box. And Byron, if you have any additional comments, please provide them. Okay, so yes, it was a great presentation. Thank you, Glenn. We will be providing this presentation just like we are all of the presentations. If we are having audio issues, although Byron, we might be able to hear you. I think I hear your computer clicking.
Yeah, I think you do.
Yay! Okay, do you have any comments you want to share to finalize it?
And you know, it's hard on the presentations like this to try to keep them short enough to get through all the information, because there's a lot of topics. You know, I've had this thing broken into 5 separate presentations before, so I hope everybody was able to get a good overall picture of what, you know, we're trying to achieve, and some areas that you can focus, you know, to do your best on these buildings. If y'all have any questions now, you know, feel free to put them in the chat box. If you want to hit me up by, you know, phone or email or through Tima, feel free.
So Glenn is typing. We'll let Glenn type. We are going to go into the happy hour after this, the networking. We're starting a little late because the other one that you probably hear Cami on over there went a little long. So I'll let you guys finish typing. Yes, good continuous commissioning information. This was the only presentation that we had on continuous commissioning type ideas and stuff, so it went well. Byron, I want to thank you for everything you did in putting this presentation together for us. We will do the happy hour networking through Zoom. If anybody would like to join us, we will be over there. We will, Byron. And if speaking of that, if you guys have anything that you want to, if you have something, a topic you guys want discussed, the attendees, please let us know and we will see what we can do. Oh, we got a question, Byron. What's your opinion on heat wheels?
So when it comes to wheels, that usually ends up being an owner preference on the maintenance side. So we have, if you're specifically referring to energy wheels, there's some places where we end up using them. Most of the owners that we're working with, they usually ask us to design around not using them because they don't want to mess with the maintenance later on. But you know, there are places where they work well. Most of like I said, most of the school people they're more interested in either trying to avoid those, or a lot of times we'll use like a heat, which is a static device. So you know, they have their place, but you just got to be willing to do the maintenance on them.
Are there any other questions at this time?
All right, guys, well, that's it. Oh. With that, I think we're just going to wrap
Glenn keeps showing that he's typing, but I think he's just clicking there. So I'm going to go ahead and close it out. We will see you guys in the happy hour networking. If not, we will have coffee networking in the morning, and then we'll start the sessions at 8:30 again. And we will also have some expo hall time. So thank you guys so much for joining us today.
Thank you.